the concept like this clipper circuit is basically going to clip off some portion of the waveform, some portion of the input waveform that we are providing as an input. Okay, so it is clipping off some portion of input voltage. Okay, so in this respect we have seen the series clipper. So next is parallel clipper. So as it is the like parallel clipper, that means the diode that we will be using will be connected in parallel with the load resistance. So here there will be a load resistance. So this is the circuit, equivalent circuit you can represent it. So a diode connected in parallel with the load resistance. So whatever voltage across the diode will be there, the same voltage will be across the load resistance. So either we are getting the output from the load resistance, or it is similar to we are getting the output from the diode. Across the diode, whatever the voltage is there, that will be the output voltage. Okay, so from there you can just see if we are providing a square wave pulse. Okay, so here we have, in case of positive half and negative half, we will just consider whether the diode is on and off. So this is the case where the diode is basically an ideal diode. So if it is ideal, it will be either open circuit or circuit based on the biasing of the diode. So in case of we are applying the positive input voltage, positive for the positive half of the input voltage. So once we are applying the positive, the diode will be on. Okay, so once diode is on, that means it will be behaving like a short circuit. So once this diode is short circuit, the output at the output terminal basically will be like it is short circuit, so output will be 0. Okay, so for the case when diode is on, the output will be 0. Okay, so next we will see in the negative half. So in the negative half, when the diode is connected with the negative voltage, so once it is connected to negative voltage, it will be behaving like an open circuit because it is reverse bias. So once it is reverse bias, it will be behaving like an open circuit. So once it is open, so here in off case, so the circuit will be like this, and here it is open circuit, and we are getting the output from here plus minus, and this is the resistance, and here we are providing the input. So if it is open, that means the current flowing will be 0. So there will be no current flowing, means voltage drop across this resistor will be 0. So voltage drop across the resistor will also be 0. So that's why whatever input voltage we are applying, the same input voltage will be appearing at the output. Okay, so whatever input voltage we are applying, the same input voltage will be appearing at the output. So from there we can just see like we are just clipping the positive portion of the waveform. So positive portion of the waveform is being clipped off. In the negative, we are getting the same voltage, input voltage that we are applying. So similar case we can see in case of triangular pulse we are applying. Then the next we will see like, so here with two different examples we can get the output like it is clipping the positive half. Okay, so it is clipping the positive half. Similarly, we have an example circuit like here we are getting input. This is the input waveform, and this is the circuit. So here we are getting the output here. So first of all, we need to analyze like from where we are getting the output. So we are getting the output with between these two terminals. So that means there is that load resistance connected. Okay, so here load resistance is connected, or we are just seeing like it will be the voltage across the diode along with this supply voltage. So this is an example where we are including the external supply voltage also. Okay, so along with the diode. So here one more thing you can just see. So in the previous case, the diode direction was like it is this way. So the diode direction is like here, the output we are taking from the positive terminal, and negative output terminal is connected to the negative half or n type for the diode. But in this example case, the diode is placed in opposite direction. So if it is placed in opposite direction, that means whenever we are applying the positive voltage to the input, this will be like a reverse biasing. Okay, but initially it is having some voltage. So suppose we are having a diode connected in this configuration, so that we are applying the input. So input, suppose we are increasing with 0, so with respect to time it is increasing with 0 and reaching to 16 volt. Okay, so in between that, suppose below this 4 volt, below this 4 volt, this diode will be forward biased because the external voltage is being applied. So this positive voltage is connected to the P type of the diode. So till the 4 volt is applied by using this input waveform, the diode will be on. Okay, so what would be the level of this transition voltage? To calculate the transition voltage, we use this circuit. So here, like, if we need to find out like what will be the transition voltage at which the circuit is going to on and off, so that will depend on, like, we, to calculate that, we have to first see like there is a zero current flowing. So initially when this will be like off, there will be a zero current, but at that time we will be sorting this diode. So if zero current is flowing, the voltage drop across the resistor will be zero, and the voltage drop across the diode is also, we have considered, zero. In that case, we will see like what will be the input voltage at which the diode will be like, it is going to switch from off to on or on to off. Okay, basically we are going to switch like at what voltage we will switching. So by calculating here, we can see like the input voltage is coming out to be 4. Okay, that means at 4, by using KVL through this, you can get like input voltage is coming out to be 4 volt. So at 4 volt, this uh, condition of switching will be taking place in this circuit. So up to 4 volt, so once we will be drawing the output with respect to that, we can see like we will be drawing this 4 volt level. This will be the transition level, so at which the diode will be switching on and off. Okay, so from there, so up to when we are applying the voltage 0 to 4 volt, so if we are applying the 0 to 4 volt, this diode will be on because this is constantly connected with a 4 volt DC voltage. So this 4 volt DC voltage will be turning this diode on. So once this diode is on, the voltage across, means it is on, that means it will be short circuited, and the output will be directly connected to 4 volt. So till 0 to 4 volt, we will be getting the output like a constant voltage, that is 0 to constant 4 volt voltage. Okay, once we are applying input voltage greater than 4 voltage, so once we are applying the input that is greater than 4 voltage, beyond this 4 voltage, that means once it is high, so this diode will be like whatever the effective voltage, we can see like here plus 4 voltage is applied, but here plus, suppose it is 5 volt, so if it is 5 volt, so here 5 volt is applied, here 4 volt is applied, so this diode will be behaving like a reverse bias. Okay, so now as we are going to increase the input voltage beyond this 4 volt, the diode will be in reverse bias. So if it is reverse bias, it will be behaving like in off age case. Okay, so this is the region when the diode will be off. Okay, so if diode is off, that means it is open circuit. Okay, so if it is open circuit, there will be no current flowing. Okay, so no current flowing, and this voltage that we have applied, that will be a different case. Okay, like it will not be affecting at the output because it is open circuit. So this output is now directly connected to this input itself. So in case of off state, we can just see what is the circuit. So here input voltage will be there, and the diode is off, that means open circuit, and a voltage here connected. So if it is off, the current will be 0. So when current is 0, the voltage across the resistor will be 0. So this will be the output voltage. So now this, there is no connection in between that, so there is no role of this 4 volt supply voltage. That output is directly connected to input now. So for the case when diode is off, whatever input voltage is there, the same will be appearing at the output voltage. Okay, so in this region case there is the output voltage between that will be ranging from 4 volt to 16 volt. Okay, so this will be the output voltage. And again, in case of the voltage, like beyond, once we have reached the maximum, now we are decreasing, and as we are switching from 4 volt to less than 4 volt, now the diode will be on. In that case, when diode is on, this will be having like short circuit. When there is short circuit, some current will be flowing. Okay, some non-zero current will be flowing, but that current flow does not be affecting the output, because output now directly connected in parallel with this 4 volt. Okay, so always the output will be 4 volt when the diode is on. So always, so below this uh, 4 volt transition level, this diode is on basically here in this region between here to here, it is on. So in that case, when it is diode is on, it will be having a constant voltage, that is 4 volt, so it will be giving this out the output. Okay, so this is one of the example, like how we should be analyzing. So in the above case, it was positive clipper. Okay, we are clipping the positive half of the input waveform. Now in this case, we are clipping the negative half, we are getting the positive half. Okay, also suppose if this diode that we are using is a practical diode, then the circuit will be behaving like, so if the diode is practical, so instead of when it is on, so if diode is practical diode, it is on, then it will be behaving like a constant voltage source, that is 0.7 volt if it is silicon. Okay, in on case, in off case, it will be again open circuit. So this is the case of practical diode. So here the practical diode, if we are using, then when the diode is really on, in that case, so from there we can get the output, like what will be the output. This is the output in case of practical case, if the diode is practical. So here, when the diode is on in the practical case, so when this diode is on, so overall we can see the voltage will be like here it is negative and positive, and positive and negative is in opposite direction. So overall voltage that we are getting into output will be the sum of these voltages, like uh, if we consider the KVL. So suppose we are applying the KVL, you can just analyze the KVL. So for KVL, we will be saying like, first of all we need to have each component with this positive and negative sign. So once we have that, we can start, like suppose from any terminal we can start. So from 0.7, suppose we are starting, so it's exiting current, exiting terminal is basically negative, so we will be writing negative 0.7. So because this is the current direction, we can move in the correct direction only. So here we are moving, so exiting voltage is negative, so negative V naught. So again we are moving here, so exiting voltage is plus, it is plus 4 volt is equals to 0. So from there we can get like V naught will be equals to 4 volt minus 0.7. So output waveform that we will be getting is 3.3 volt. So here when that diode is on, at that time this output voltage will be not 4 volt, it will be 3.3 volt. Okay, and when this diode is off, whatever input voltage is there, that will be at the output. And again this will be the case where this is total maximum 16 volt and the minimum will be 3.3 volt. So this is the case in case of practical diode. Okay, so this is basically the clipper circuits. So this is the summary of clipper circuit, the complete we have seen. So we can just summarize the clipper circuit. So this clipper circuit we have seen, it is having series and parallel configuration, series clipper and parallel clipper. So if it is series clipper, that is having an ideal diode. So in case of we need to have a positive clipper, we can see this as the circuit, so it will be clipping the positive. If we want to implement the negative clipper, we will just change the direction of diode. Okay, so once we have changed the direction of diode, this will be considering the next type of clipper, that is negative clipper. So it will be clipping the negative half and retaining the positive half. Okay, so next is series clipper with some voltage. So we are including some voltage. So if it is, this is the case of positive clipper. If we are including some voltage, that means the clipping will be taking place, but we are going to have like this extra voltage that we are applying. So this voltage, if we are applying like, if we are applying in opposite with the input, so input is suppose plus and v, plus and minus, here it's opposite we are applying, then at that time it is having like this waveform is completely like it is clipping again the positive side, but in the negative side it is increasing. So whatever the negative, whatever voltage we are applying, it will be maximum voltage will be maximum voltage Vm plus this V voltage. Okay, because this was the positive clipper, the diode direction indicating it is positive clipper, so positive half will be clipped off, but the maximum in negative side will be increased by, because in negative side suppose we are applying the negative, then it will be negative and positive. This will be the sign of the input voltage. So here this negative and this negative is in same direction. So at the in negative side, the maximum voltage that we will be getting is Vm plus V. So in the negative half, we will be getting this as the voltage. Suppose we are applying the voltage such that it is in opposite direction. So as it is in for the positive half, it is in same direction, but in negative half, it is in opposite direction. But in it is positive clipper, so in negative direction the output, suppose this is negative direction, so in negative and it is positive, so it is in opposite direction, so it is maximum voltage. So in negative direction the output that we will be getting is maximum, this will be the minus because it is in opposite direction, minus V. Okay, so whatever V is there, Vm, whatever the maximum voltage there, less than V, so it will be reduced by V amount, it will be reduced, so it will be only Vm minus V. Okay, so this will be the case in case of uh, positive clipper with supply voltage that is in opposite direction. Okay, so this will be the output. Similar case is there in case of uh, clipper, that in case of negative clipper. So here this is the case, if it is negative clipper and in positive direction it is of opposite direction, so it is positive. In case of positive half, it will be plus and minus, and it is here plus and minus, that means it is in opposite direction. So if it is in opposite direction, or the output, we will be getting the output that will be V maximum minus this V. So V maximum minus V, that will be your output. So if we change the sign of this supply voltage, then it will be in positive half, it will be in same direction. So if it is in same direction, we will be getting V maximum plus V. Okay, as the output. That means you can just see, we have just added a DC, extra DC, and once we are adding the extra DC, then we are clipping. So you can just intuitively know like, so this was the input waveform. It is positive clipper, that means in negative direction it will be in same direction. So in negative, like we are just increasing its DC value, so we are just shifting this to, this is the DC value is 0. Now we are changing the DC value to negative value. So instead of this, we will change this waveform to negative side with V direction. So if we do that, so instead of 0, it was 0, but now the across this V volt, the waveform will be like that, and the 0 will be here, somewhat here, 0 will be here. So now here we are clipping the positive, so now we are clipping this portion. If we are clipping this portion, the remaining portion will be this that we have obtained. Okay, so this is the remaining portion will be only this one, this 0 and this and this. Okay, so this is the remaining portion if we, in this was the case. So we have just changed the DC value. Okay, so we are here, initially it is 0 volt DC, so DC value was 0. Now in this case the DC value we have changed to minus V. We have shifted it downward and then clipped off. So here it is shifted upward by plus V. We are now in this case shifting the waveform upward and then clipping off. Okay. So this was the case of series clipper. Similarly, similar analysis we can do in case of parallel clipper also. So if it is parallel clipper, output will be taking place at the voltage across the diode. So it is positive clipping. This is the positive clipping. Positive portion has been clipped, and this is the negative clipping. So in negative clipping, the only difference is here the diode direction is this way, and now the here in case of negative clipping, the diode direction has changed. We can obtain this. Similarly, positive uh, and negative clipping with a biasing voltage. So here a biasing voltage along with voltage output diode is there. Okay. So if we are having the biasing like it is in same direction, in suppose it is in case of positive, so we are applying the plus V voltage, and here in case of the same direction with respect to output, so it will be output will be like started with shifting, and it is positive clipping, so positive portion will be clipped and negative will be here. Okay, so output will be shifted like at this voltage. So similarly we can get in case of negative, like instead of getting 0 when it was 0, instead of 0 it is getting minus V volt, and then it is having the remaining portion of the input waveform. Okay, so this is the case where we are clipping the positive as well as the negative half. Okay, this is an I can say advanced case. We are clipping the positive as well as negative in the same direction, in the same circuit. Okay, so this is sometimes questions are asked in the similar question have been asked in gate also. You can just see the previous year gate papers, how it is working basically. So here it is including the concept of uh, the positive and a negative clipper at the same time. Okay, and this is the case where negative clipping is when done with parallel clipper. Okay, so the next we will see is clamping circuit. So up to here we have seen the clipper circuit. Now we will see what is clamper circuit basically. So here the clamper circuit is basically, as the name suggests, it is clamping the voltage. That means whatever DC voltage is there, suppose any waveform is there, its DC value is 0. So in this case the DC value of the voltage is 0. Okay, so in clamping circuit either it will be a positive clamper or a negative clamper. So if it is positive clamper means, if this is the input waveform, we are going to clamp this output to a level that is uh, greater than 0, we can call it like here the DC voltage is 0. So in case of positive clamper, if this is the 0 level, we will be, suppose we are having clamper circuit, it will clamp the input waveform to a voltage that is higher than, we can see from here like what is the, this is the maximum voltage plus Vm. So the maximum voltage is plus Vm and the minimum voltage is minus Vm. So from there we can see what is the maximum and minimum. The difference between maximum and minimum is called swing. So how the voltage is changing in positive and negative. So it is changing to up to maximum Vm, and in negative direction it is changing to minus Vm. So the swing in the waveform is, it is swinging between plus Vm and minus Vm. So total swing is this. So total swing is, this is Vm and this is Vm, that means 2 Vm it is swinging. So the swing in this input waveform is 2 Vm, and the frequency, suppose this is the frequency, I suppose it is AC signal having a 50 Hertz frequency. Okay, and also the DC level is 0 volt. So this is the input waveform. Now if we are going to use the clamper circuit, what it will do is, in positive clamper it will be clamping this waveform to positive side, and suppose this clamping is with respect to plus Vm case. So we are clamping to plus Vm DC value. So initially the DC value was 0. Now we are clamping, or we can say like we are adding the DC, or this circuit is also called uh, DC translator basically. So it is also called DC translator circuit. Okay, so we are translating this 0 DC level to plus Vm DC level. So here the swing in that case will be nothing but, if we are changing this waveform to above side plus Vm direction, the swing will be again the same, like the minimum value will be 0, the maximum value will be 2 Vm. So the swing is again 2 Vm, and the frequency again the same. Whatever the input frequency is there, the same will be the output. But in case of the DC value, so here the DC value was 0, but now the DC value is plus Vm. So this is the case of uh, positive clamper. So in case of negative clamper, so in case of negative clamper, we can just see the waveform. So here this is the 0 voltage level. With respect to time, it is varying. So this is 0. So now it has clamped to minus Vm side. Okay, that means it has been included with a DC voltage that is minus Vm. So this waveform will be shifted like this. Okay, so the minimum value that is there in this case is minus 2 Vm, and the maximum value is 0. So the what is the swing is here basically? So the swing here is again the 2 Vm. So maximum minus minimum, that is 2 Vm, and the frequency again here is the same 50 Hertz, but the DC voltage level will be here is minus Vm. Okay, so this is your negative clamper. This is your negative clamper, and this is your positive clamper circuit. Okay, so basically this clamper circuit is going to uh, clamp the circuit, or it is going to add the DC voltage or DC level to the circuit, and it is not going to affect on the waveform properties, like what is the nature of the waveform, that is not going to affect its nature, but it is going to only affect its DC voltage level. Okay, so either it is going to increase the DC voltage level or decrease the DC voltage level. If it is increasing the DC voltage level, it is called positive clamper. If it is decreasing the DC level, it will be called negative clamper. Okay, so to realize this clamper circuit, basically we will be using uh, capacitors along with the load resistance, or the resistance that of the circuit that we are going to have. So basically it is divided into two different types, negative and positive clamper. So we will see how it is going to behave. Okay, so just see an basic clamper circuit. So here this is the configuration of clamper circuit. So we are getting the output across this diode. We are getting this output across this diode, and at the input terminal, whenever we are connecting the input, it is coming out to with a capacitor. A capacitor will be connected, suppose in series with this diode. So this is capacitor in series with the diode. So with respect to that, whatever voltage across the diode is there, we will be getting that output voltage. So this R is nothing but the load resistance here. Okay, RL we can call it, or R we can just call it. Okay, so here, so how the analysis of this will be taking place is, basically we need to find out like at what voltage this diode is going to turn on and off. Okay, and also this is a capacitor. So the property of capacitor is it stores charges. Okay, so that means this capacitor will be having the property of it is charging uh, or discharging, or it is storing the charge basically. So if it is going to store the charge, it will be called like charging of capacitor. If it is uh, losing its charge, it will be called discharging of capacitor. Okay, so if whatever input voltage we are applying, it is also connected to capacitor. So either it is charging or discharging, or what is the rate of charging and discharging, that is basically defined by the tau, that is called time constant in case of capacitor. So time constant in case of capacitor is basically given by the capacitance multiplied by the equivalent resistance. Whatever equivalent resistance of the circuit is there, that multiplied by the capacitance, that will be coming out to be a time constant. So if your time constant is high, if time constant is high, okay, so if time constant is high, that means the charging or discharging will be low. If time constant is high, that means the charging time or discharging time will be low. Okay, that means if we are going to have a high tau, this charging and discharging of the if tau is high, basically charging and discharging will be not a decreasing, we can say like it will be low. If tau is low, we can say like charging and discharging will be high. So the rate of charging and discharging basically will be low. That means the time taken to charge and discharge will be low or high based on the time constant. So in the circuit, before analyzing, we need to also consider the time constant of this circuit. Okay, so how this time constant is going to affect the charging and discharging, we will also see that. So here the basic concept initially, what we do is the capacitor is initially considered as like uh, having zero voltage. So that means at initial we are going to analyze the circuit. This voltage across this capacitor is considered to be a 0 volt. So that means if this is a 0 volt, so whenever we are applying the input voltage, that is in positive. So if positive voltage is applied, so this was the case of diode. So if positive voltage is applied, this diode will be on. If diode is on, at that time the voltage across this diode will be coming out to be 0. So output voltage will be 0 once the diode is on. So once this diode is on, at the time initially we have considered the charge across this capacitor is 0, but as this diode is on, the voltage is connected to the capacitor also. So this voltage, so the input voltage will be charging this capacitor. Okay, so it will be charging this capacitor. Okay, so in this case the rate of charge is like tau. So tau will be, so if it is a diode is forward bias, that means the resistance across it is will be a forward resistance. Okay, so this forward resistance through an ideal diode is coming out to be 0. Okay, so if it is 0, so the equivalent resistance will also be a 0. So the tau will be C into R. Okay, so R is here basically 0. So tau is 0. Okay, so initially when tau is 0, when diode is on, so tau is 0 means the time constant is 0. That means the charging time, that means the rate of charging of capacitor will be very high. That means initially the capacitor is having 0 voltage, so it is voltage across this will be 0. But as the diode is on, it will be making the diode this circuit like output will be 0 if diode is on. But at the other time, the charging of this capacitor will be taking place with very high rate. Charging will be very high if tau is 0. Okay, so in other case, like if it is in reverse bias, so once it is charged, this there will be, so this in positive half, this is positive half. So in positive half, it is charging of capacitor is there, the same charge will be appearing at the capacitor. Okay, same charge will be appearing at the capacitor. So now in the reverse case, when it negative voltage is applied the input, so this is negative and this is positive. In this case, diode will be off. When diode will be off, the voltage across this output voltage will be coming out to be like the voltage of the capacitor along with the voltage of this input voltage. So input voltage will be added to capacitor voltage. Okay, so the output we will be getting V output in case of when diode is in reverse bias, the output voltage that we will be getting is input voltage along with the voltage of the capacitor. So at the output we will be getting, so if it is positive in the positive half, the maximum voltage that will be appearing at the capacitor will be the V maximum that we have applied. So the maximum voltage that we can get at the output in reverse case is the maximum voltage of input, that is Vm, plus the maximum voltage of the capacitor, that is Vm. So that is coming out to be 2 Vm. So the output voltage at the uh, case of when diode is reverse bias, we will be getting 2 Vm at the output. So just to be making the summary like how this charging and discharging is going to affect the output waveform. So it's like here in case of when diode is on, the charging is very high, so it will be high such that for half of the time period when we are applying the positive half, the diode will be on. At that time, the output that we will be getting is 0 because the diode is on, so output voltage will be coming out to be 0. But till t by 2 time, the diode this capacitor has been charged to what is V, whatever maximum voltage is there, that has been charged by the capacitor. So in the next negative half, as we are applying the negative half, the diode will be open circuit, but at the output we will be getting the input voltage that is in reverse bias case. So this is negative minus Vm along with the voltage that have been charged by the capacitor. So charge the output voltage in the reverse case we will be getting is minus 2 Vm. Okay, so this will be the output waveform in case of the clamper. Okay, so here it is looking like we are just clamping this negative portion to 2 times. We have, based on the clamping, in the clamping we are clamping this waveform in the negative direction. Okay, or we can just see like we have shifted this to downward. Once we are shifting this to downward, that means this has been coming out to be 0, and overall the swing here is 2v. 2v was swing. In case of here also it is 2v. Whatever frequency is there, the same frequency is here. The only difference is here the DC value is 0, but here the DC value is basically minus v maximum vm, or we can call it, it is coming out to be the same v, whatever the v is there with respect to that. So it is clamping the input waveform from 0 DC to some DC that is in negative. Okay, so this is nothing but the negative clamping. Okay, so just to get this, we can just summarize like how this clamping is being done. So or just before summary, just we can get like, so we can analyze the circuit, how this is going to behave. So suppose we are having the first case like negative clamping. So just we can summarize it like, so in negative clamping we are having a circuit, that is capacitor along with a diode is there, and here a resistance is connected, positive and negative input voltage we are applying. This is the capacitor, and from there we are getting the output. Okay, so in that case, initially we will be considering like the VC is 0 for negative, V0 negative means just below the 0 time period time, and just above the 0 time period it is coming out to be 0 volt. So if it is 0 volt, then means it will be short circuited and this diode will be in on case. In that case, like we will be representing initially this capacitor is short circuited. Okay, so for positive half of input, basically this diode is on. So in positive half the diode is on. So this is the case of input voltage. Now we will see like how it is varying. This is the output voltage and this is your input voltage. Okay, so for suppose this is the complete t time period, so this is t by 2, this is t time period, and this is t by 4 time period. So for the positive half, once we are applying the positive half, uh, the tau we can see like the tau that we will be having is like the diode is on, and in that case the tau will be whatever the forward resistance is there in parallel with the R or load resistance is there, multiplied by the C, or we can see like it is forward bias, so this forward resistance will be very less. So what in this two parallel, whatever the less will be there, that will be coming out to be there. So it is RF multiplied by C. So this will be very less than the time period of the input waveform. Basically it is very less than in the time period of the input waveform. Therefore the rate of charging of capacitor uh, is very high. So if this is the case, that means up to the time period of t by 4, so up to this time period the diode will be on and the capacitor up to t by 4 time period has been charged. So here, so up to here it is on, that means it will be the same like it will be a 0 volt. So up to t by 4 it will be 0 volt, and after this t by 4 this has been charged. Okay, so after this the t by 4, that now that input voltage is reducing, and also the capacitor has charged. So the output waveform that we will be getting is, it will be also be reducing, but we have charged this to maximum Vm. So now till this point the diode will be on in that case also, but uh, it will be like it has maximum V, and at this point it is maximum Vm also here, maximum voltage, so this is Vm. Okay, so as we are reducing the input voltage beyond Vm, so now this is positive and negative. Okay, but we are, it is in positive, but we are reducing, so this will, the diode will be in reverse bias beyond this region. So beyond this region it will be in reverse bias case diode. From here to here it was in forward bias case. Okay, because at this point the capacitor voltage is also Vm and the input voltage is Vm at there, but as we are decreasing the input voltage, the capacitor voltage is Vm itself. So overall voltage across this diode will not be a positive value, because that voltage will be Vm of the, or we can say like the capacitor voltage minus this input voltage. So input voltage is now less than Vm. So the overall voltage that we will be getting is the negative here. So this is negative voltage, the maximum voltage that is negative. So it is connected to here. So it is negatively connected, will always be there, even if we are reducing this Vm below this. So below this, whatever voltage we are reducing, this will always be connected in reverse bias case. So from here there, it is reverse bias. So it is open circuit now. So if it is reverse bias, it is open circuit. So whatever voltage will be there is whatever input voltage there with respect to plus Vm, this is there. Okay. So this input voltage will be coming out to be like the same waveform is. Okay. So up to here it will be the Vm. Okay. So now it will be coming out to be negative direction, and then it will be moving this way. Okay. So this will be the waveform, and now in the case here, now up to here it will be the maximum, and then it will be again moving here. So this will be the waveform nature. Once in case of positive case, and in case of similarly in case of negative. So add to Vm at time period t by 4 itself, it will be in reverse bias case. So in reverse bias case, why this capacitor will be considered as a constant plus Vm voltage, or it is being constant, it will not be decreasing, or rate of discharging basically of capacitor will be very high, that's why it is considered to be a constant voltage. Okay. So at v at t by 4 time period, as we have, if we consider at t by 4 time period, we have considered like V input is nothing but the Vm, and the capacitor voltage is also Vm. Okay. So in that case, if diode is on at or we can call it up to t by 4, the output will be coming out to be 0 up to this t by 4. Beyond this t by 4 time period, the diode will be off. Beyond t by 4, the diode is off. So if diode is off, the time constant will be like, if it is off, there will be a resistance that will be in reverse bias. So it's equivalent like it will be represented by a reverse bias resistance. Okay. So the time period in that case will be like, and here it is plus and minus Vm, that will be behaving like a constant voltage source. Okay. The capacitor, and here we are applying the input voltage, and here we are getting the output. So, and also there is a resistor here connected, that is load resistance. So the tau will be the R, that is reverse bias resistance, in parallel with RL multiplied by the C. So as this R is very high and this is low, so if low and high resistance is connected in parallel, so low resistance will be the significant one. So this is coming out to be RL into C. So this tau will be here RL into C when the diode is off or diode is in reverse bias. So this RL into C, that is time constant, that will be uh, coming out to be like, it is uh, greater than or very greater than time period. So that means your time constant tau is very high. Okay. So that means the time constant is very high, it is implies like the rate of discharging. So if tau is very high, that means the rate of discharging of the capacitor will be very small. Okay. Time period is very time constant is very high, then the discharging of capacitor will be very high, means it will be discharged, uh, capacitor will be discharged with will be discharging very small, that means its discharging rate will be very small. So even if like for constant or whatever this time period is there, for this time period the rate of discharging of this capacitor will be very small, so it will be reducing its voltage by very less value. That means it will be considered like the capacitor will be capacitor will be behaving like a constant voltage. Okay, so as the diode is reverse bias, the time constant will be very high, so the rate of discharging of the capacitor will be very less. That means it will be discharged by very less value, so it will be behaving like a constant voltage source. Capacitor will be like a constant voltage source in case of reverse biased diode. Okay, so if it is a reverse bias case and the diode is reverse bias and the capacitor is voltage source, so the output voltage that we will be getting is like a addition of input voltage and the Vm value in case of reverse bias. So that's why we are getting the higher voltage swing in case of the negative case, negative direction. Okay, so we can just summarize it like, if input voltage is there, and what will be the output? So output voltage will be V input minus the Vm. Okay, so if we summarize it, if the input voltage is Vm, in that case the output that we will be getting is 0. If the input voltage was 0, we were getting the output minus Vm, and if the input voltage is minus Vm, we are getting the output that is minus 2 Vm.